It's not rocket science. Except, it literally is. And you're about to understand it. All of it. Okay, so here's the thing. That phrase, "it's not rocket science," exists specifically to mean this is easy. People say it when they're filling out a form, or assembling IKEA furniture, or trying to figure out if a tomato is a fruit. The implication is that rocket science is the hardest, most impossibly complex thing a human brain could attempt. And for most of history, sure, fair enough. But here's what nobody tells you. The core idea behind getting to space is actually something you've already felt in your body. You've already experienced the physics. You just didn't know it was rocket science at the time. So what is a rocket, really? Why does it go up instead of just sitting there looking expensive? Okay, think about the last time you were in a pool, or a lake, or a bathtub, no judgment. You put your hands together, pushed water backward, and your body moved forward. That's it. That's the whole thing. Newton's third law: every action has an equal and opposite reaction. A rocket engine isn't magic. It's just throwing stuff backward, really, really hard. The rocket expels hot gas downward at insane speed, and the rocket goes up. That's it. You are now 10% of the way to understanding how humans left the planet. But here's where it gets interesting. Throwing stuff backward gets you off the ground. That part's easy. The hard part, the actually brain-breaking part, isn't going up. It's staying up. Wait, staying up? Like, in orbit? Isn't that just going really high? No. No. This is the single biggest misconception about space. Orbit has almost nothing to do with altitude. Almost nothing. The International Space Station is only about 250 miles above the surface. That's the distance from New York City to Boston. You could drive that in under 5 hours. If you dug a straight tunnel through nothing and just went straight up 250 miles, you wouldn't be in orbit at all. You'd just be really high up, and then you'd fall straight back down. Hard. Fast. Badly. So what makes something actually orbit? Speed. Sideways speed. Obscene, almost incomprehensible sideways speed. The ISS isn't just sitting 250 miles up, it's moving sideways at roughly 17,500 miles per hour. That's about 5 miles every single second. Wow! To put that in terms your brain can handle, if you sneezed in New York at that speed, you'd be in London before you finished the sneeze. And here's the mind-bending part. The part that sounds like a philosophy problem, but is actually physics. At 17,500 miles per hour, the ISS is falling. Constantly. Every second of every day, it is falling toward Earth. But the Earth is curving away beneath it at exactly the same rate. So it falls and falls and falls and never lands. It's just perpetually missing the Earth. Orbit isn't defying gravity. Orbit is falling so fast sideways that you keep missing the ground. You've basically been playing this game your whole life without knowing it. You ever play Angry Birds? Or literally any game where you throw something and it curves in an arc? That arc, that parabola, is what happens when a projectile moves forward while also falling downward. Orbit is just that. But so fast that the arc matches the curve of the entire planet. You're not above gravity. You're surfing it. This is the thing that blew Newton's mind when he thought about it in 1687. He imagined a cannon on top of an impossibly tall mountain. You fire the cannonball. It curves and lands. You fire harder. It curves and lands farther away. You fire hard enough, and it curves and curves and curves and comes back around behind you. The cannonball is now in orbit. Same cannonball. Same gravity. Just more speed. So the entire point of a rocket, the whole goal, is not to go up. It's to go sideways, fast enough, while also not slamming into the atmosphere on the way. Vertical is just to get you above the thick part of the air. Horizontal is everything. And how hard is it to actually hit that speed? Well, this is where the phrase, "it's not rocket science," really starts to collapse. Because getting to 17,500 miles per hour from a dead stop, while also fighting gravity and atmospheric drag the entire way up, while also carrying enough fuel to actually do it, is one of the most brutally difficult engineering problems ever attempted by our species. Which brings us to the equation that basically governs all of modern spaceflight. It was written down in 1903 by a Russian schoolteacher who had been deaf since childhood and who never saw a rocket launch in his entire life. His name was Konstantin Tsiolkovsky, and the equation he derived in his bedroom is still, today, the fundamental limit on what rockets can do. It's called the Tsiolkovsky rocket equation, and when you see it, it looks simple. It is not simple. It is, in a very real sense, the villain of the entire story of space exploration. So here's the equation. Delta V equals exhaust velocity times the natural log of the ratio of wet mass to dry mass. That's it. That's the whole thing. Looks fine, right? Looks manageable. Looks like the kind of thing you'd find on a high school physics worksheet between a problem about pulleys and a diagram of a ramp. It is not fine. Delta V, which everyone in the space business just calls Delta V, is your budget. Not your money budget, your velocity budget. It's the total amount of speed change a rocket can make over its entire lifetime. Everything in spaceflight is priced in Delta V. Getting to low Earth orbit costs about 9,400 meters per second of Delta V. Getting to the moon costs more. Getting to Mars costs a lot more. And every single maneuver, every burn, every course correction, every orbit adjustment takes a bite out of that budget. Run out of Delta V, and you are done. You are a very expensive piece of space junk. Okay, so how do you get more Delta V? You either burn your fuel faster, that's exhaust velocity, and it's mostly a chemistry problem, or you carry more fuel. Sounds easy. Just carry more fuel. Problem solved, right? Here's where the equation becomes the villain. More fuel means more mass. More mass means you need more thrust to lift it. More thrust means more fuel to generate that thrust. More fuel means more mass, which means more fuel, which means more mass. This is called the tyranny of the rocket equation, and it is exactly as bad as it sounds. It's a feedback loop from hell. Every kilogram of payload you want to send to orbit requires roughly 10 to 20 kilograms of fuel on the ground. 10 to 20. For every single kilogram, that coffee thermos you want to bring to the ISS, and it's bringing along a couple dozen kilograms of rocket fuel as its emotional support animal. This is why rockets look the way they do. A fully loaded rocket on the launch pad is something like 85 to 95% fuel by mass. The actual spacecraft, the thing you care about, is a tiny fraction at the very top. The rest is just fuel and tanks to hold the fuel, and engines to burn the fuel, and structural supports to hold the tanks, and more fuel. It's fuel all the way down. A rocket is basically a flying fuel tank that briefly also contains astronauts. So engineers came up with the single most elegant hack in the history of transportation: staging. Here's the idea. You build the rocket in sections. The bottom section is huge. Mostly fuel tanks, massive engines. It burns all its fuel, gets the rocket moving fast, and then, and this is the part that's borderline brilliant, you throw it away. Just detach it, let it fall, forget about it. Now your rocket is suddenly lighter because you're not dragging around dead, empty tanks and engines you don't need anymore. You light the next stage's engines. That stage burns its fuel, gets you faster still, and then you throw that away too. By the time you reach orbit, you've shed almost all the dead weight. All that's left is the spacecraft. This is why Elon Musk's engineers celebrate so hard when a rocket stage lands back on a drone ship in the ocean. Because instead of throwing away a piece of hardware that costs somewhere between $10 and $60 million, they caught it. They can use it again. That's not just cool, that's the difference between spaceflight being economically feasible or just a very dramatic way to burn money. SpaceX has had a few extremely dramatic ways to burn money. You may have seen the videos. The engineers have a technical term for it. Rapid unplanned disassembly, which is genuinely what they write in the official report. Rapid. Unplanned. Disassembly. I love aerospace engineers. Never change. Okay. Here's the awe moment. I'm not joking around right now. Put down your phone. Well, you're reading this on your phone, so don't do that. But pay attention. The Voyager 1 spacecraft was launched in 1977. It weighed about 1,600 pounds. It has been flying continuously for nearly 50 years. It is currently over 24 billion kilometers from Earth. That's so far that a signal traveling at the speed of light, 186,000 miles per second, takes over 22 hours to reach it. And it's still sending data. Right now, as you watch this, a 1970s era computer roughly as powerful as a pocket calculator is sailing through interstellar space, billions of miles past the edge of the solar system, in the cold dark between the stars, and it is still talking to us. The antenna on the ground has to be pointed with extreme precision just to pick up its signal, a signal with less power than a refrigerator light bulb. Well, we are listening to a refrigerator light bulb from 24 billion kilometers away and hearing it. That's not a metaphor. That's what we actually did. And Voyager 1 got that far, not just from its rocket. It got that far because of a trick. A trick that sounds like cheating but is completely legal in the universe. It's called a gravitational slingshot. Or, if you want to sound like you work at JPL, a gravity assist. And understanding how it works requires understanding one thing about orbits that most people never learn. Orbits aren't static. They're negotiable. When a spacecraft flies close to a planet, the planet's gravity pulls on it. Obviously, but here's the thing that makes your brain itch if you think about it too hard. The planet is also moving. It's orbiting the sun at its own speed. And when a spacecraft swings around a moving planet, it doesn't just get bent, it can steal some of that planet's orbital momentum. The spacecraft speeds up. The planet slows down by an infinitesimally tiny amount. We're talking like a fraction of a millimeter over billions of years. The planet doesn't notice. The spacecraft, though, it rockets forward. No fuel burned. Free speed. Completely from the laws of physics. It's like drafting behind a semi-truck on a highway, except the semi-truck is Jupiter and you're a spacecraft the size of a car. NASA mission planners mapped out Voyager's trajectory specifically to slingshot around Jupiter and Saturn, gaining speed with each flyby. 1 rocket launch, 2 gravitational boosts, and a spacecraft that will outlast every human institution currently alive. That's the kind of long-term planning that makes you feel something. Voyager 1 won't be stopped by budget cuts. It won't be cancelled. It's just going. So now you understand the whole picture. You want to get to space. Step 1. Go sideways fast enough to fall around the planet forever. That's orbit. Step 2. Manage your delta V budget like it's the last $20 before payday. Step 3. Throw away everything heavy the moment you don't need it anymore. Step 4. When you need to go farther, borrow speed from planets that will never miss it. That's spaceflight. That's the whole thing. But wait, we haven't talked about actually landing anywhere. Because getting somewhere is one problem. Getting there and not arriving at several hundred miles per hour into the surface is a different problem. Mars has a thin atmosphere, thin enough that it barely slows you down, thick enough that you can't just ignore it. The moon has no atmosphere at all. You land on the moon the same way you'd land anywhere in a vacuum, using rockets to slow yourself down. You burn engines pointed at the surface, and you hover, and you lower yourself gently and hope that every single piece of software and hardware is doing exactly what it should. In real time. Autonomously. On a 1.3 second communication delay from Earth. That's what engineers mean when they call landing on the moon the 7 minutes of terror. Except on Mars, it's closer to 7 full minutes where the spacecraft has to handle everything alone, because the signal delay means mission control can only watch. By the time they see something going wrong, it's already over. The spacecraft is already on the surface, either gently or in several rapidly disassembled pieces. And here's where the video game comparison comes full circle. Because if you've ever played Kerbal Space Program, and if you haven't, you're missing arguably the best physics teacher ever accidentally made. You know that the moment you truly understand orbital mechanics is the moment the game stops being frustrating and starts feeling like you're cheating. You realize that to slow down in orbit, you burn forward. You realize that to raise your orbit on one side, you burn at the opposite side. You realize that rendezvous isn't about chasing another spacecraft, it's about matching orbits, meeting in the middle, letting gravity do the dance. And every person who has ever played that game has had a moment, usually around hour 15, where they look at a rocket trajectory on a screen and just go, oh, I get it now. That moment. That's the actual goal. Not the rocket. Not the Delta V budget. That moment of suddenly seeing the shape of something that seemed impossibly complex and realizing you can hold it in your head. That's why humans went to space. Not for geopolitics, not for resources, not even for science, though all of those mattered. Because we are a species that cannot see a thing and not want to touch it. We pointed at a light in the sky, and we built a metal pipe, stuffed it with controlled explosions, and pointed it at the light. 46 times. Before we got it right once. And then we walked around up there like it was always something we knew we could do. The phrase, "it's not rocket science," is supposed to mean easy. But what it actually means, now that you know, is that rocket science isn't magic. It's not mystical genius locked away in the brains of a few chosen humans. It's Newton's pool trick, plus a math equation from a deaf Russian schoolteacher, plus the audacity to actually try. It's falling toward a planet and missing it on purpose. It's throwing away your fuel tanks mid-flight and celebrating when one lands on a boat. It's a refrigerator light bulb talking to us from the space between the stars. And here's the question we still haven't answered. The one that keeps the people who build these things up at night. We know how to get to orbit. We know how to get to the moon, Mars, the outer planets. We know the physics cold. But here's what we genuinely do not know. Whether there is a fundamental upper limit to how fast any physical object can travel through space, and if there is, whether that limit makes it mathematically, permanently, physically impossible for any civilization, anywhere in the universe, to ever reach another star system within a single human lifetime. We don't know. We actually don't know. Which means either interstellar travel is impossible for biology, or we are missing something enormous about how the universe works. And if that's not worth a follow-up video, I don't know what is.